Every star that ignites the cosmic dark, every planet that orbits in silent grace, the very atoms composing your hand, they all exist in flagrant defiance of an obvious and terrifying collapse. Classical intuition suggests that matter should collapse, relentlessly pulled inward by its own fundamental forces until it becomes an unimaginably dense, featureless singularity. At the grandest scale, gravity, the master architect of cosmic structures, is a force of pure attraction. It pulls galaxies together, it forged the sun from a cloud of gas and dust, and it pins you to the earth. There is no off switch. It is a constant, universal summons to come closer. If gravity were the only story, the universe would be a brief, violent flicker, a cosmic firework that immediately implodes back into the point from which it came. But the threat is even more intimate, operating within every single atom. Inside that microscopic domain, the electromagnetic force holds sway. A dense, positively charged nucleus yanks on its cloud of negatively charged electrons with a force vastly more powerful than gravity. Classical physics would predict a grim, instantaneous outcome. Electrons should spiral into the nucleus in a fraction of a second, radiating away their energy and neutralizing the atom into a tiny, inert nub. If this were true, the universe would be a soup. There would be no atomic structure, no electron shells to facilitate the beautiful dance of chemistry. No molecules, no water, no DNA, no life. The vibrant, complex tapestry of reality we perceive would be replaced by a bland, homogeneous cosmic sludge. Yet, we are here. We exist in a cosmos of breathtaking structure and stability. Atoms are not tiny, doomed solar systems. They are resilient, well-defined entities. Stars burn for billions of years, held in a delicate equilibrium. The very ground beneath our feet is solid, resisting the immense gravitational pressure of an entire planet. This glaring discrepancy between what should happen and what happens is one of the most profound paradoxes in all of physics. It points to a missing rule, a hidden law operating beneath the surface of classical reality, a decree so powerful it can stare down the barrel of gravity and electromagnetism and win. This silent, invisible force preventing universal implosion, this cosmic edict that forces particles to maintain their distance, is known as the Pauli exclusion principle. It is not a force in the traditional sense, like gravity or electromagnetism. It is something deeper, a fundamental rule of quantum etiquette, an unyielding statement about the nature of identity and space at the subatomic level. It is the universe's most profound antisocial law, and without it, nothing we know would exist. The question, then, is not merely academic. It is the most existential question we can ask. How does this seemingly simple quantum rule single-handedly prevent cosmic catastrophe and enable the very existence of everything? From that chilling possibility of universal collapse emerges the elegant solution, a quantum decree formulated by the brilliant and notoriously critical physicist Wolfgang Pauli in 1925. At its heart, the Pauli exclusion principle is breathtakingly simple in its declaration, yet cosmic in its consequences. It states that no two identical fermions can occupy the exact same quantum state simultaneously. They simply, fundamentally refuse to share the same existential space. This isn't a suggestion, it's a non-negotiable law woven into the very fabric of reality. To understand its power, we first have to understand its subjects, the fermions. The universe of particles is split into two great families. On one side, you have the bosons, the socialites. These are force-carrying particles like photons and the Higgs boson. Bosons love to be together. They can and will pile into the exact same quantum state, overlapping and reinforcing one another. This is why you can have a laser, where countless photons march in perfect lockstep, creating a coherent, powerful beam. On the other side, you have the fermions, the ultimate individualists. These are the particles of matter, electrons, protons, neutrons, and their constituent quarks. Fermions are governed by the exclusion principle. They are fundamentally antisocial and demand their own unique space. But what is this quantum state they refuse to share? It's best imagined as a particle's unique cosmic address, a set of 4 quantum numbers that precisely defines its properties within an atom. First is the principal quantum number, which describes the electron's energy level. Think of it as the city the electron lives in. Higher numbers mean higher energy and a greater distance from the nucleus. Second is the azimuthal quantum number, which defines the shape of the orbital, the subshell. This is the electron street. It determines if the electron's path is a simple sphere, a dumbbell shape, or something more complex. Third is the magnetic quantum number, which specifies the orientation of that orbital in space. This is the house number on the street. Finally, and most crucially for the principle, is the spin quantum number. A fermion, like an electron, has an intrinsic property called spin, a form of quantum angular momentum. It can be either spin up or spin down. This is the final, unique identifier, the name of the resident in the house. The Pauli exclusion principle dictates that no 2 electrons in the same atom can have the exact same set of these 4 numbers. This is the mechanism that saves the universe. Consider a simple helium atom with 2 electrons. The first electron can settle into the lowest energy state, city 1, street 0, house 0, with its spin up. Now the second electron arrives. It can also move into city 1, street 0, house 0, but only if it has the opposite spin down. Its address is now unique. The lowest energy level is full. When a third electron arrives, as in a lithium atom, it finds no vacancy. The principle forbids it from squeezing in. It is to occupy the next available energy level, a higher shell further from the nucleus. This process repeats, building up the elements 1 electron at a time. This antisocial behavior is precisely what gives atoms their structure, creating the elegant shells and subshells that dictate all of chemical bonding. This is the origin of the periodic table, the reason we have metals, gases, and the carbon that forms life instead of a universe of indistinguishable atomic mush. The consequences of this quantum standoff scale up to astronomical proportions. When a star like our Sun exhausts its fuel, it collapses under its own gravity. It shrinks until it becomes a white dwarf, packing the mass of a sun into a sphere the size of the Earth. What stops it from collapsing further into a black hole? The Pauli exclusion principle. The star's electrons are crushed together so tightly that they begin to fill up every available low-energy quantum state. To crush the star further would require forcing multiple electrons into the same state, which the principle forbids. The electrons push back, creating an immense outward pressure known as electron degeneracy pressure. It is a quantum shield against the infinite crush of gravity. But what if gravity is even stronger, as in the collapse of a much more massive star? The gravitational force becomes so immense it overcomes even electron degeneracy pressure. It mashes electrons and protons together to form a city-sized ball of pure neutrons. This is a neutron star, one of the densest objects in the cosmos. A single teaspoon of its material would weigh billions of tons. Here, gravity is at its most brutal, yet the star remains stable. Why? Because neutrons are also fermions. They too obey the Pauli exclusion principle. They resist being forced into the same quantum state, creating an even more powerful neutron degeneracy pressure. This single, quiet quantum rule is the only thing standing between the neutron star and total collapse. From the shape of a single atom to the survival of a dead star, the Pauli exclusion principle is the silent guardian, the invisible architect, ensuring that the universe doesn't just exist, but thrives in spectacular, stable diversity.